Section: Introduction. In this section, we aim to enhance the reasoning abilities of large language models, LLMs, for complex tasks. We introduced the chain of thought, COT, approach to leverage ILMs in context learning skills. However, LLMs often struggle with mathematical reasoning due to errors in numerical calculations, known as the hallucination issue. To tackle this, we developed the Program of Thought, POT, framework and Program-Aided Language, PAL, models. These models use an external code interpreter to handle precise numerical and symbolic computations, aiming to improve ILM's accuracy in complex tasks. The COT and POT frameworks rely on self-consistency majority voting, which differs from how humans approach mathematical problem solving. Humans tend to reassess and adjust their solution path when facing mistakes, unlike these frameworks that focus on reaching the final answer regardless of intermediate accuracy. To address this, we explore the Tree of Thoughts, TOT, framework, which is useful for tasks requiring strategic planning or search. Our work extends the Tree of Thoughts research beyond LLM inference by integrating LLMs with the Monte Carlo Tree Search, MCTS, framework. This integration balances exploration and exploitation, generating high-quality training data without human annotations. This approach has been successful in board games like AlphaGo, where AlphaGo Zero autonomously evolves its strategies using MCTS without human input. In mathematical problem solving, whether through text analysis or coding, a logical structure is crucial. While COT and POT models require manual annotation by domain experts, we believe well pre-trained LLMs have the necessary mathematical knowledge. Our research focuses on autonomously generating solutions in the React format using a well pre-trained LLM with improved prompts and an MCTS framework. We assume that the correctness of the LLM's predicted answer correlates with the quality of the solution process. Errors flagged by the code interpreter indicate low-quality solutions. Our training data includes question statements and final answers, unlike in games like Go where the final board configuration determines the outcome. The value model in the MCTS framework evaluates the quality of intermediate reasoning steps. We present an iterative training approach on the math dataset, known for challenging math problems. Our results show that integrating LMs with the value model and MCTS framework can autonomously generate high-quality math reasoning data. The value model helps the policy model navigate more effective solution paths. We break down the solution process into reasoning steps and view mathematical problem solving through reinforcement learning. The policy model, represented by an LLM, guides the transition between states in each reasoning step. Our goal is to develop a step-level value model to assess the correctness of partial solutions and guide subsequent reasoning steps. Rewards are assigned based on the correctness of final answers, and Monte Carlo evaluation is used to train the value model. Section Summary. In this section, we introduce the chain of thought, COT, approach to enhance large language models' reasoning capabilities in complex tasks, focusing on in-context learning. However, in mathematical reasoning, these models face challenges due to calculation errors, leading to the development of the Program of Thought, POT, framework and Program-Aided Language, PAL, models. By integrating an external code interpreter for precise computations, these frameworks aim to improve accuracy and reliability in reasoning tasks, unlike human problem-solving processes that involve reassessment and adjustment of solution paths. Section: Our method. In this section, we introduce our method. In the traditional Monte Carlo (MC) evaluation approach, conducting multiple simulations from each state can be inefficient. To address this, we suggest using the Monte Carlo Tree Search (MCTS) algorithm, which allows for reusing simulations and updating estimated values effectively. To implement MCTS evaluation, we utilize a value model v_phi_k and an LLM policy model pi_theta_k. With these models, we develop an inference algorithm powered by MCTS. This algorithm starts at the initial state and expands the search tree by adding new nodes based on the potential of states, guided by policy and value networks. The MCTS algorithm involves 4 key operations: selection, expansion, evaluation, and backup. During selection, actions are chosen based on the upper confidence bounds applied to trees, UCT, principle. Expansion involves determining the next possible actions. Evaluation assesses the value of a node using a weighted sum. Backup updates the values of nodes along the path to the leaf node. After running multiple simulations with MCTS, we obtain a tree storing action state values. By approximating the value using this tree, we can train the state action value model iteratively. The training process involves pre-training the LLM as the policy model and updating both policy and value models using a multitask loss function based on correct and incorrect solution paths sampled from the MCTS tree. By iterating this training process with each round of MCTS, we aim to enhance our models for improved performance. Section Summary. In this section, we introduce a method that leverages the Monte Carlo Tree Search, MCTS, algorithm to efficiently evaluate mathematical problem-solving scenarios. By utilizing value and policy models within the MCTS framework, we iteratively grow a search tree to identify high-potential states and make informed decisions. Through a series of key operations including selection, expansion, evaluation, and backup, our approach refines the value estimation process and enhances the policy model for improved decision-making in subsequent rounds of MCTS iterations. Section: Inference. In this section, we simplify the Monte Carlo Tree Search, MCTS, inference process to a more straightforward version called step-level beam search. We start by generating a set of actions using a language model, LLM, and then evaluate these actions using a value LLM. We select the top actions and repeat this process iteratively. This method allows for practical output generation in real-world scenarios. We conducted experiments to enhance the mathematical reasoning capabilities of large language models without human annotated solution processes. We used the DeepSeek MathBase 7b model, trained on math-related data without fine-tuning. Our training set included 15K question-answer pairs without solution processes. We tested our approach on different datasets and evaluated the accuracy using a math evaluation toolkit. To generate solutions, we used the MCTS framework without human annotated solutions. We iteratively trained our models and generated detailed solution processes. We compared our approach with other models, including proprietary and open-source ones, as well as supervised fine-tuning models using external tools. Our results show that our approach, AlphaMath, performs well without relying on high-quality solutions annotated by humans or GPT-4. We achieved improvements in mathematical reasoning abilities, especially for challenging problems. By utilizing a step-level beam search, we improved performance gradually. Our method demonstrates competitiveness with state-of-the-art models on large language models. Section Summary. In this section, we simplify the Monte Carlo Tree Search, MCTS, inference process by introducing step-level beam search, which eliminates the need for complex backups and makes the inference more practical for real-world deployment. We experiment with enhancing mathematical reasoning using large language models without human annotated solutions, training on math-specific data and employing MCTS to generate detailed solution processes efficiently. Our approach, AlphaMath, showcases competitive performance without relying on high-quality human or GPT-4 annotated solutions, demonstrating effectiveness in both in-domain and out-of-domain scenarios. Section: Analysis 1. Problem-solving rate of MCTS. In this section, we assess the success rate of MCTS in solving problems over multiple rounds. We used the math dataset, which classifies problems by difficulty and subject, to calculate the problem-solving rate across different categories. In our training set, we counted how many problems were solved in any of the paths within the 10 trees we built. Our results showed that MCTS was more successful in solving harder problems in later rounds. Additionally, MCTS showed improved ability to solve a wider range of problems across different subjects as the rounds progressed. However, in round 3, we noticed that the improvement was not consistent for all difficulty levels and subjects. In fact, for easier problems, the performance even decreased. This inconsistency led us to stop our iterative training after round 3. Moving on to the inference strategies, we explored how our model performed under different strategies such as greedy decoding, step-level beam search, and MCTS. Our findings indicated an overall performance improvement with more training rounds for all strategies, both in domain and out of domain. Specifically, we observed that increasing the beam size B_1 in step-level beam search led to better performance. Although MCTS showed the highest performance, it was computationally intensive and time-consuming. We compared the average problem-solving duration and the number of intermediate steps taken on the math dataset for each strategy. MCTS required the longest solving time and the most steps due to our specific configuration. To achieve similar accuracy, step-level beam search with certain parameters was more computationally efficient. Interestingly, a larger beam size B_1 tended to reduce the average problem-solving duration by decreasing the number of steps needed. When discussing majority voting, we found it challenging to directly compare it with step-level beam search due to their different methodologies. Majority voting involves generating 5 complete solutions considering all intermediate steps, while step-level beam search generates multiple candidates but retains only the top one. The mechanics of candidate selection and retention differ significantly between the two methods. In our analysis of the value model, we plotted the distribution of Q values for intermediate steps from the third round of MCTS on our training dataset. Correct solutions had Q values skewed towards 1, indicating high probability density near 1. Incorrect solutions had a less skewed distribution with density leaning towards -1. We found that correct intermediate steps could lead to both correct and incorrect final answers. Therefore, during simulations, the Q values of intermediate steps in incorrect solutions could also be updated with a reward of 1. In summary, our work leveraged question-answer pairs data to enhance the performance of our model through a self-improvement iteration strategy. We integrated the value model with the generative model to improve decoding strategies like step beam search and MCTS, providing a richer set of decoding options.